Welcome back, everyone, to Cybersecurity with Python and the Microbit. This is day 2 of 3 in the workshop. I'll go ahead and again paste in the link to the Google Slides. Previously, I pasted the bit.ly link. Here is the official link into the chat. Paste. Okay, and just a reminder that if you have a single monitor, it can be helpful to click to wiggle your mouse in front of the screen and click the view button that appears up top, and then select exit full screen. And again, this is if you have only one monitor. After exiting full screen, you can then tile your windows so that you can watch what's going on in the workshop and do some things in the Microbit Python editor. And then also, if you have a laptop, and this may even be true for some desktops, do try to maximize your performance setting so that it can keep up with the 2 Microbit Python editors and Zoom all at once. Today we'll start off with Q&A and discussion. If any questions came up for you between now or the previous session and now, please feel free to unmute and ask them or type them into the chat. Either way is fine. I'll do a very quick review and then we'll dive into encryption with starting with the simplest of, or the most probably well-known and simplest of all classical ciphers, the Caesar cipher. Then we'll kind of we'll expand that to ASCII and then look at substitution ciphers. And this is part of a sequence within the cybersecurity lessons that has gradually increasing levels of encryption, although admittedly none of them are particularly high, but using really strong encryption in the microbit can end up taking quite a bit of space and being ruling out the use of microbit version 1, which doesn't have as much storage as the microbit version 2. Then we'll move on after the encryption to sniffing attacks and defenses. So we'll see some examples of how that can work, and then how the threat can be mitigated, and the microbit network hardened against such attacks. Last but not least for the day, we'll look at brute force attacks, and then your homework will be to make sure you can get to the Educator site. So that's essentially part of learn.parallax.com, where you go and log in as an educator, and then you can get access to the assessment materials. So jump in with questions at any time, and that includes in the chat or by unmuting yourself and asking. So in review, on day 1, we focused on the computer science foundation that we'll build on today with cybersecurity examples. And so the computer science foundation was just the basics of scripting. And then we're going to be using a number of these scripting basics in applications. A little bit more underpinning we'll be establishing with talking about the microbit radio and how to set up a radio network with microbits. But after that, we'll go into the encryption intro, sniffing attacks and defenses, brute force. We'll probably put off malformed packets to Friday. And then on Friday, we'll also be talking about some other ways to either expand the cybersecurity lessons, like, for example, with the Cyberbot robot as a vehicle for learning with some of the cybersecurity concepts, applying them to a robot, as well as getting into the educator resources, which I might have already said. And then upcoming workshops, just a reminder of that. We talked about that on day one, how to purchase microbits, cyberbots, and otherwise. And I should really emphasize that with the educator resources, we'll be looking at a number of, we'll be recapping where to find stuff at Parallax, and then also some other resources that are available that you might find to be useful for your students, including like the Make It Coded site that we looked at the first day, final questions and answers and wrap up, and that'll be it. Okay, so again, we talked about the computer science lessons, and then for homework, we did the bidirectional text application. And so that was something where even though we're connected to the same computer, and even though it's going from 1 microbit into the computer and eventually to the terminal, it's not going from this terminal through the computer to this terminal. What's happening is if you type something here, it will go to the microbit, and then it will go out the microbit's radio antenna, which is, if you look at the underside, it'll usually be a squiggly line that's in the upper left. At any rate, so your message gets sent out the radio, and any microbit that is in the same channel, that's a radio frequency that it uses, and a group setting will be able to receive that message and send it to the computer via USB, where, and presumably it's connected to a different computer in your computer lab or in your classroom. So with students with Chromebooks, for example, it might not be a computer lab. At any rate, they will see the incoming message and can type something back, and it goes the other direction across the radio waves and into here, and then through USB to the other computer's serial monitor. So before we continue, let's make sure that we've all got that working. And so what I'd like to do is, you've probably already got the bidirectional communication example running, and we can restart that. What I'd like to do temporarily is just run a test and have everybody note which microbit is microbit A, and then which microbit is microbit B. So I'm sending out 2 programs here, or 2 scripts through the chat. And so we'll have you put 1. So I just sent the first script, and then here's the second script. So we'll have you put 1 in 1 microbit Python editor. Like here we are with display.show A, and then that displayed over here on the left in this microbit, and then display.show microbit B, and that one is displaying here in the microbit on the right. And just make a note of which microbit is A and B. For example, I'm going to have to remember that the as opposed to fumbling around for a pencil and some masking tape or whatever, I'm going to try to remember that the microbit with the yellow trim is the A microbit, and then this one is the B, and then also I'll try to remember that this tab is A and this tab is B. And again, these are things that we don't usually have to do in a classroom because it's usually 1 microbit connected to 1 computer. All right, so has everybody got an A and a B? I would like to see some thumbs up or some confirmations in the chat. 1, 2, 3. Good job, people. 4. Anybody need help? or a little bit more time? 5? Well, we've got 5 out of 9. 6, good. 7. Okay, so again, just give me a shout out if you need a little bit more time. And so now we'll move on to getting that bidirectional texts resumed. And this is mainly for demonstration purposes. You almost certainly already have it running, but I'm just going to follow the bidirectional texts link in the slides. And that takes us to near the end of Radio Basics. And then we'll go ahead and copy that in. And just make sure our microbits are able to talk to each other. And I have something to mention about that too. So this time I'm going to remember to print that this is microbit transceiver A, so that looks good. And then in the other window, I'm going to change this one to microbit transceiver B. And then we'll go ahead and tile the screen. Now it's important to tile the screen because I guess I better just, well, that's unexpected. I got a web USB error, and if I run it again, it went just fine. All right. So here it now identifies itself as microbit A, and on this side it identifies itself as microbit B, and you can drag the separator up. And the reason I'm doing this tiled side by side is because if you're going back and forth between tabs, I've noticed that the serial monitor clears itself, and so you can't necessarily see the history of the chat. And so it is important for this application to have both serial monitors visible and to go back and forth between them. If you're connected to a single computer on this workshop in the classroom, that of course doesn't matter, but so we'll make sure that that everything works. Do computers disapprove when you anthropomorphize them? That's a question this begs. At any rate, let's see. Finally, I got both A and B. There was a connection error with one. Yeah, I got a connection error too, which was kind of funny. And again, during the previous the session 1 workshop, what I found I had to do, and if I had any glitches getting them connected, was I had to unplug both microbits and then close any windows or tabs that had the microbit Python editor running. Then after reconnecting both microbits and then reopening 2 tabs going to the microbit Python editor, I was able to make the connections. And so that is at the tail end of the Monday workshop. For anybody watching this later, just look at the tail end of Monday's workshop and you'll see how that works. Along with me struggling a little bit to get them reconnected unsuccessfully until I did that complete clean slate approach after having a single one connected for a while. Backtracking a little bit about the radio. So we skipped to the end of the radio chapter, and to do bidirectional texts. the way it gets started is, first of all, talking about the radio that, and this is an older revision microbit. Your chip will be probably at a diagonal as opposed to horizontal. And this antenna will also probably be at a diagonal right here. At any rate, there's a little squiggly trace on the printed circuit board that functions as the antenna. And then here's the oscillator, the main microcontroller for the microbit. And the radio feature is built in. There are two visible, oh no, not those traces, because those are going to the oscillator. Yeah, there's somewhere along here, there's going to be a trace going up to the antenna. At any rate, this is 2.4 gigahertz. That is a band that's used by Wi-Fi, Bluetooth, and many other devices. They have to get an FCC license to sell products that run at this frequency. And then it is legal for users to operate those products without having any kind of radio operator's license, because everything is taken care of by the manufacturer. And so again, and it talks about all these things, that it's the 2.4 gigahertz band. And also there are frequencies within the 2.4 gigahertz band. So that's 2.4 trillion oscillations per second that the radio makes. And sorry about that, billion. Anyway, these channels are each 1 megahertz wide. And so if you're using channel 0 in your script, and that is right here in the script where we're configuring it to channel equals 7. With that configuration, we're 7 channels into the band that the microbit uses. And so that is, I believe, 2.407 gigahertz. And so it'll go all the way up to 2.483 gigahertz, or 2483 megahertz. And so those are the radio frequencies that are used. So this is one way to have students, say, pair off or work in groups of 3, is to assign subgroups of students their own channel. And then that way there's not too much interference noise. Usually when I'm teaching this, I like to start off with everybody on the same channel. And then when it gets unmanageable in terms of keeping track of who's saying what in the chat window, I suggest that they pair off, or again, work in groups of 3. And then they get to see how using a different channel will prevent interference. And then also, as far as channels go, there's a feature in many devices that's both for reliability and security called frequency hopping. And so in here, the students actually change frequencies. They run a script that changes back and forth between one frequency and another, as well as a script that, well, they first see that, hey, if they use one channel and then another microbit, or if they use 2 channels to send, and another microbit is only receiving on one channel, that other microbit might only see the messages coming through from channel 7, but it'll miss the ones coming from channel 14. Or the vice versa can be the case, depending on what the receiving microbit is configured to channel-wise. And then after seeing that, then they update their microbit to receive messages from both channels. And this is a very slow motion rudimentary form of what's called frequency hopping, often also referred to as spread spectrum communication. let's see here. I think that about covers it. One thing I noticed, though, is that I'm going to have to check, because usually what's going to happen with this example is that some of the text is going to be cut off. So if we run this again, that USB error I got may have been because I tried to program these too quickly. At any rate, so if I type a longer message, the default buffer of the microbits radio is 32. And I'm thinking about updating the example script, because you can go up to, I think, like 254 in terms of the number of characters. And so if we up this to length equals 2 on both sides here, then you'll be able to send longer messages. I'm going to wait for this one to finish loading. Oh, it still had a, oh. So I made a mistake here. Okay, it doesn't like that. I must be using the wrong term. So if we go to API, which is the reference, or we could just probably go to plain old reference and find radio down here. And let's see if, okay, these are just really basic approaches. And incidentally, another way to, you can drag and drop the code from the script examples onto your editor. The way that most examples show to put students together into small groups is to have each of them set a group number. But they're still all on the default channel, which does happen to be channel 7. So they're still all running on the same frequency. And what you will see here is text collisions in a classroom. And of course, if a student mounts a DDoS attack on the group over the microbit wireless by sending continuous data in a very tight loop, you'll see quite a bit of interference. And so that's why we talk about using different frequencies and different, as opposed to different channels, or pardon me, we use different channels. Those are frequencies as opposed to different groups. But the group part is nice because it's kind of like a network setting that's on the same channel, so that students can see that even though they're all on the same channel, if they set their group number differently, that's another way to discover how to have some a level of privacy in their conversations amongst each other. Okay, so let's see if I can figure out why this length equals 250 is something that I didn't remember correctly. Microbit radio. Here it is. Config. So we'll show more about config. There is also an address setting to make the microbit. If you use both address and group, you will have it'll be very difficult for another student to find your conversation. So channel, power, address, group. Oh, it's not even showing length. Does anybody see it? config, data rate, group, address, power. I'm looking for length. Oh, there's length. So the default is 32. Oh, 254 is too high. Might be 253. That's the max. There we go. Okay. Sorry about that. 250. And now if we run that same test, we're not cut off at 32 characters anymore, but we will be cut off at 250, or I think there's like 2 characters of header in that. So it might be something like 248. So if you have students asking you, hey, how come the whole string doesn't come through? Now you'll know the answer, and Control A, C, and I'll go ahead and paste this modified script in so you can just keep a copy of it in the chat. There we go. Again, feel free to jump in with questions at any time. So that is radio basics. And essentially, we're just transmitting texts back and forth. Now, when it comes to data, sure, a string can be considered a packet, even if it's just a text data. But what this does is this activity shows a use of dictionaries. So on day 1, we talked about strings. And why do I not see the shortcut for strings and characters? Okay, learn.parallax.com, cybersecurity, strings and characters. So, so this part is what's expanded on in the exchanging texts. And then there was also a computer microbit talk example that we looked at on day 1. Where we entered a number to start counting from and something to say after the countdown is complete, and then it did that. Well, one thing we can do, and that is done to emphasize how data is often transmitted over the internet in JSON data, which again is something that most browsers use to exchange simple data like search entries and stuff like that, is the dictionary, because the dictionary actually has the same key value format as JSON data. And so here is a distributed countdown example. And so these are 2 things, incidentally, that students will want to use what they learn a little bit later in the cybersecurity lessons. 2 things that the students will want to be able to protect from various forms of cyber attacks. And so the first is the chat, and then the second one is a countdown application, which they can also make more interesting or turn it into some other app if they are so inclined. So let's try this out. Let's try out this unencrypted, currently, countdown app. And let's see here. Send and receive data packets. Yep, I'm on the right spot. So I'll go ahead and give you this link. Paste. And what you'll want to do is take the countdown sender and put it into 1 microbit. And I'll actually just paste these in. paste. So there's countdown sender that you'll want to put in 1 microbit. And then here is countdown receiver for the other microbit. Paste. Okay, so they're both in your chat. And now I need to copy those into my microbit editors. Copy. Okay, so I think this was microbit B. Yeah. Okay, so here's microbit A. I'll make that the sender. Control A, Control V. That selects all and then pastes over everything. It's kind of a shortcut to shading and then right-clicking and pasting. Copy. Control A, Control V. Okay, so now I have my sender and receiver, and this is another one where you will need to tile your browsers so that you can see both of them at the same time. And then we'll go ahead and load our sender microbit and our receiver microbit. And there was a question that came up before the workshop started. I didn't quite get a chance to respond to it. The question was, with the text exchanging application that we just finished, were we supposed to be able to see anything on the microbit LED display? So were we supposed to be able to see anything on here? And the answer is no. And the way to check that is to take a look at what your microbit is using to communicate. Here it's using print, and print is the function that sends its output to the display, as does input. Although input, of course, takes data from the display, but it also has, in many cases, a built-in prompt that it sends. So print and input, whereas anything that says display would be displayed on the 5x5 LED matrix display on the microbit. All right, so now we have our distributed application running. And so we'll type in a countdown start of 4, and then we'll use liftoff. Oops. And then all I have to do is hit enter, and then that will get transmitted out this microbit's radio into this microbit's radio, and then, well, to USB to this microbit, out its radio, into this microbit's radio, and then out of its USB and into the computer. So when I hit enter, it displays the countdown. So here's our distributed countdown app. And if anybody asks what this would be useful for, well, one thing would be a remote model rocket launcher. And it could also essentially trigger various other events. For example, in animatronics, it might move an animatronic hand or head or jaw to make it look like it's talking, something like that. All right, so this is another thing that students will want to protect, but along the way, it's also a reinforcement of the use of dictionaries. I kind of glossed over it. The previous lesson was a reinforcement in the use of strings. And then here we are using dictionaries. And so on these lines, the dictionary is created. It's actually done a little bit differently from the original lesson in that this time an empty dictionary is created, and then fields are added. What do those fields look like after they added? Well, we can see what is sent here. It's actually, after the dictionary is created, it's converted to a string using the str function. And this is all talked about in the lessons. So don't worry about it. I'm just kind of trying to point out highlights of what is learned and taught, as opposed to trying to impart everything on you. Anyway, so it's this it starts as a dictionary, but at this point it is converted to a string stored in a variable named packet, and then radio.send is what sends that packet out. And by the way, notice that here the length is increased slightly, just to make sure that there's enough room for whatever text is being sent. And there's lots of extra room. I could up that by 5 times, up to 250. So it gets sent with radio send. It gets sent as a string. Over here on the other side, it gets received as a string and stored in a variable named packet. And then this while true loop here repeatedly checks for an incoming packet. So most of the time, it'll get back nothing, and radio.receive will return a data type of none given to packet. And so this statement right here is saying, well, skip it if packet's none, but if packet's not none, we've got some work to do. Now, another way to do this is simply if packet, and then implicitly, if it's none, it skips it. And if it's anything other than none, it will go in and do some work. So it prints the packet that was received. And again, that's all this right here. And then eval is a way of taking a string that contains Python statements and turning that string into Python, or the actual Python statement. So as opposed to text representing a Python statement, it will convert it into a Python statement or object. And so the string containing all this gets converted to an actual dictionary here. And then on the receiving end, so this might be like the server, if a web browser sends it a message, it will go and it will look in the dictionary for something labeled, or the start key, and it'll find the value 4 and put that in value. And then it'll go hunting for the after key, and it'll find that, and it will put the liftoff string into the message variable. And then it prints both of those, and then it essentially does the same thing as it did earlier when only one microbit was used while students were learning how to use the terminal. So that's item 2 of things to protect with your microbit, and an introduction of radio data. Encryption. So what we start the students with is just a nice simple example of encrypting by hand. And so we'll use the whole Caesar cipher and have them go through. Probably best to zoom in on this a little bit. We'll have them go through and say, all right, if I want to send an encrypted message, one really simple rudimentary way to encrypt it is to say, if I'm starting with the H in hello, well, I can simply count a certain number of letters to the right and substitute. Substitution ciphers 101 with the letter M in this case. And then repeating that with E, counting over by 5, we get J, which is the second letter in our ciphertext, this being our plain text up here. And so the students get to do this by hand, and it's something that they'll probably find helpful is just going through an algorithm to make sure they understand it before they write code for it. And then there's decryption, which we start with the ciphertext here of M, and then simply go the reverse direction. And incidentally, the key for all this is the number 5. And so we encrypt with the number 5 going to the right, and then decrypt with the number 5 going to the left, or we could think about it as -5 going to the right as well. Then some students might ask, well, what happens if the letter you need to encrypt is near the end of the alphabet? And the answer for that is simply to wrap around to the beginning of the alphabet and keep counting. And that works for both encryption and decryption. Next up, so this chapter goes very incrementally through. So the first thing it does is it starts with a Python script that encrypts one letter. And it builds upon something that was learned in the strings chapter, which is that you can give a string a name, and then you can use that string's name in Python and then .find and find a particular letter. So it will go and look for M, this alpha.find of letter, will count over the number of letters, and it will give the index starting at 0 for A and 1 for B, and counting all the way up to M, which I see is 12 down here. So it will return 12 for the index. And so then they get to see, all right, well, the letter equals, and then it's the letter, and then they'll see its index in the alphabet. So this is just, it was deemed that this was probably an easier way to get started with understanding ciphers as opposed to using ASCII text. So they work to encrypt and decrypt individual letters first, and then this little picture shows exactly how all that works as I just described above. And you can, for example, take this and put it into your slideshow. Simply copy the image, put it in the slideshow, and talk about it. Then there's encrypting. So previously, that was not encryption. That was just, well, how does the index work of finding the index of a letter? Now the encryption can add a certain number to that letter. And we're continuing with that example of key of 5. And so M ends up encrypting to R. Let's see here. Oh, I apologize if I have not been pasting in links as well as I should. It looks like Ari has been pasting in links to help out. And then I'll just show you where I'm at right now in the Learn site at learn.parallax.com. All right, so anyway, this one here does the same thing in terms of finding the index, just as it did in the previous lesson, and even displaying the key. But then it adds the index to the key, and then this little tricky piece of code takes the remainder of the index divided by 26. And so, for example, if you tried to encrypt a letter near the end of the alphabet and you had that overflow, this is this remainder of dividing into 26 is what causes that wraparound that I talked about in the encryption by hand part. And I'm hoping that there's no picture of that. Maybe on the next page. Yes. And so this talks about how that works, and you can use these as visual aids in your slideshow if you want to talk to students about it. And then this also shows the whole wraparound that occurs when the percent sign, percent 26, is used right here to get us back to 0 for the letter A, and then keep on counting from there. As always, if any questions come up along the way, please let me know and I'll do my best to answer them. All right. So then we add in typing a single letter into the terminal and giving a key and encrypting and decrypting, and students have to use a negative number to decrypt and a positive number to encrypt, or vice versa if they so decide. Then this applies Caesar ciphers to whole words. And then this uses a function, which I talked about briefly as the extra piece of code above the main code that you can call out its name and it does a job for you. That was during Monday. And so here is the definition of the Caesar cipher. It's a function. And so we emphasize here that, okay, this function is written, it does the work for you, and then you can just, as a student, use it in your application. So you can say, you can get a key and convert that key into a number using the int operator. That'll take text that has digits and actually convert it into the number those digits represent. And then they'll get a string of characters, and we emphasize to use capital A through capital Z since that's what the Caesar cipher originally used. Though I think that there's a little piece of code here that actually converts all the letters to uppercase, even if students forget to use uppercase letters. And so this is a fun one. I'll go ahead and print again, this is later in the chapter, paste. So that's the link, and I'll try pasting in the text. This is a 1 microbit lesson. This is not distributed. This is just learning about encryption. And
I'm having some issues on my side, but I don't think that the chat message is coming through.
Oh, you know what? It automatically, if I receive a chat directly from somebody, it switches my, it switches me over without telling me so that I'm just chatting that person back. I didn't notice that happens. Sorry for missing you, the person that chatted me directly. And then sorry everyone for missing those links. So there is the link of the page I'm on going to everyone. And then I'll go ahead and also paste the script, and we can try that out. Oh, very interesting. There's an error somewhere in the script. Let's see here. Line 9, invalid syntax. We're missing a quote. How odd. Let's see if that's the only error. It is. Okay. Is that quote really missing? Yeah. Huh. we lost a quotation mark. That might have been in the web migration or in an update that followed it. We need to check for some other possibilities where there are two quotes right next to each other, because the result here started as two quotes next to each other, which is essentially an empty string. And then this loop right here works on decrypting each letter and putting it in the result string before returning that result string. So basically, result equals the Caesar function, where it plops in the key like 5 and the letters like hello. And so then key up here becomes 5 and word becomes hello. And then we have result, which is the empty string, and it uses the key to populate the result and then return that result. After the function is done, it comes back to here and plops the string into the result string, and then it gets displayed like so. And I will paste in the corrected script. Okay, here you go, paste. And then let's run it and see if it works. Okay, enter key 5. Enter characters, HELLO. And we get MJQQT. And then if we enter -5, and then MJQQT, hello is what it returns back. And so the students get to experiment at a slightly less onerous level, or they get at a little bit faster level here. They get to encrypt and decrypt entire words using the Caesar cipher. Spaces are not really encrypted to anything in the original Caesar cipher, but the next cipher that is introduced is the ASCII cipher. Along with a few other simple ones that are in the substitution world. Let's see here. So there are 94 printable characters in the ASCII cipher. So now you can use capital and lowercase, even though you really could in the previous version as well. And I think we can just try this one out. And you can type a whole message, including spaces here. And the page explains that with 96 or 94 options as opposed to 26 options, it makes it harder to crack the encryption, but it's still really not all that hard to crack that kind of encryption. So here's the next script we'll have you try. Control-A, Control-V. And we must be missing another quotation mark. Yep. Okay, I'm going to repost this in. Although if you're in a hurry, you can just change line 8 so that result equals 2 quotes, an empty string that's ready to be populated by the... Did that come through just now? Let me see. ASCII cipher. I don't think it came through. I'm going to try once more. Paste. Send. And then I'm checking now off screen to make sure, yeah, now result does have 2 quotes. Okay, excellent, excellent, excellent. And now it becomes even a little more natural to enter encrypted text. And now I can enter a whole sentence. So, but first you have to enter the key. I'll stick with 5, and I'll even capitalize the first one just so that we get the familiar encryption that we can verify. And then just hit enter. And here now is our encrypted text. And we can again enter -5 for the key, and then MJQQT percent FLFNS ampersand. And we get back to the original. So this is a little bit more functional and can actually be used in some other application. And one thing that's emphasized to the students is that they can just add this function and then call it. And that also provides a little extra familiarity with how APIs work, but still with the code visible as opposed to tucked away in a module, like the code is tucked away in the microbit module. All right, and that's there's a little bit more in encryption. We talk about some different classical substitution ciphers, and let's see here. So @bash is simply one where the alphabet is reversed. And then a custom cryptobit is emphasized as a really useful thing. Look at that, we're missing an opening quotation mark there too. This may have been something that occurred during our migration during Christmas break from one web architecture to another. All right, well, anyway, so that is the end of a really basic intro to ciphers, but with coding included. Some classes just teach about how to use the functions and skip it and make it a very much shorter thing. Other classes will go page by page, lesson by lesson within each chapter to talk about all these things. And it depends. Sometimes the cybersecurity bent is less concerned with what's under the hood, and the computer science with a cybersecurity component bent would be concerned with all of it. All right, so let's go ahead and take a quick break since we're at the 1 hour mark. Well, really 1 hour and coming up on 2 minutes. So we will reconvene at 7 past the hour. Welcome back. We are coming back from a 5-minute break, and we are now continuing onward to talk about sniffing attacks and defenses. And for anyone who guessed that encryption might play a role in the defense, you guessed correctly. So we'll start with, I should probably mention that these tiles are a link to the cover page of what I've been referring to as the chapter. And then if it's showing the cover page here, which it is, that's also a link to the cover page. But what we do here is we go to, in this case, the first page within the chapter. And if I can get back out a little bit. Okay, maybe that was too far out. And so here is the chapter. And this time, we'll be using display methods to display images on the 5x5 LED matrix display. Now this one we're going to have to kind of do using a little bit of imagination because in the classroom, we might split the students up into groups of 3, and we might be having one transmitter sending out an unencrypted message, and then the intended receiver will see that message, but the student who is taking on the sniffer role will also be able to see the same message. And so we only have 2 microbits, so we will initially just make like we have the microbit for the student who is transmitting and the microbit for the intended receiver student. And I just pasted in the link to the page we're on, and then here is the first script. And here is the second script. And thank you again, Ari, for letting me know I was not posting to everybody earlier. Now you should all see these scripts being pasted in. Okay. So run this one and run that one. Now there are things going on. Oh, yeah, I didn't do that quite right. Let's see what's going on here. Okay, so this is the image sending, which I meant to be over here. Okay, send a microbit. Okay, now I've got both microbits transmitting and no microbits receiving, which, unlike direct electrical connections, is not as potentially problematic. Okay, so now we have the receive images going on. And we can see that every time something that's sent, it's received. But in this case, we are also using the microbits feature for the receiver, at any rate, to be able to display the images that it is receiving. The transmitting student will only see it in the terminal, and they can experiment with the script a little bit to get it to both display in the terminal and in their own microbit, which is fine. But it allows to say, okay, now it's sending frown, now it's sending angry, now it's sending happy. So here is one example of sending 3 different emoji. And now we have the intended receiver. And then imagine, all right, the sniffing receiver is running the same script, and they've found the channel that the other students are on, and there's no group or address configuration added. Which so if we add a group, there's 256 options, by the way. Group equals, so I could say 128 as an example, and then I could also make the conversation even harder to find, and both sender and receiver would have to do this. You can say address equals 1 million, for example. No commas. And there are, I believe, 4 billion addresses. So that's that would make it really hard to find the conversation. We were talking about this when the recording was off, and I just thought I'd mention it, that those are ways that students can further harden their network. But for the sake of a lesson and an example, we're trying to make it at least a little bit more open. and show how the opportunities are taken at kind of a rudimentary level as opposed to getting extra sophisticated about it. Let's see here. Okay, so so we imagine, first of all, that this is the transmitter, this is the receiver, the intended receiver. Then we imagine, okay, here's the transmitter and the sniffer roll. Well, they can still see the communication that's going on. And so that is a successful cyber attack. And so they're not necessarily happy about that. And so what we want to do now is add some encryption. So this is the share something personal unencrypted with a question mark afterwards. And then later on, there's the share something personal encrypted version. And it's a little bit longer because they're using, in this case, the Caesar cipher, because these emoji are fairly simple single word things. So it's a nice opportunity to just put the Caesar cipher in use. And then later on, for encrypting texts, we'll use the ASCII substitution cipher, where it's shifted. So I just pasted in the transmitter and the receiver script for you to try this out. Oh, wait. Okay, so hold up. What we want to try first is running just the encrypted transmitter script, because it demonstrates a couple of things about encryption. So what we'll do is, here's my transmitter, I believe. Yeah, this is radio send images. So, so let's imagine next that, okay, I'm going to put the corrected transmitter into the serial monitor. There was, again, a missing quotation mark in the script. So here is the corrected transmitter. I'm going to have to go in after this is over and fix all those. Okay. Okay. So I'm going to run just the encrypted transmitter. And imagine now that this microbit, the sniffing microbit, is the receiving microbit. Imagine that that's the sniffing microbit for a second, and watch what happens when I run the encrypted version. An exception occurred, which means that the sniffing microbit has been stopped in its tracks. It's not going to sniff any more messages because it had a list of expected messages and it didn't get those. And so so it's no longer sniffing. It's no longer even able to sniff. Not just that the text is ciphertext, that it isn't plain text. It's now that the microbit stopped working until you restart the script. But even then, you might only see one. Like, for example, I'll restart this microbit by pressing and releasing this reset button on the underside next to the USB connection. And when I press and release that, I did get one encrypted message before the unhandled exception occurred. So next up is, all right, so what about the intended receiver, and we're going to come back to the sniffer because the sniffer is not going to be that easily deterred. Okay, so hold on, I gotta, I'm going to edit this in my microbit Python editor before pasting it over. Okay, adding the quotation mark, Control A, Control C, over in the chat, Control V, there you go. Now the intended receiver is decrypting using a key that was shared offline in this case. And so they can, and for the sake of example, we're displaying both the encrypted and decrypted text on both the sending and receiving end. And so the intended receiver is in sync with the transmitter in terms of the emojis it's displaying on the LED matrix display. As I mentioned, hackers are not so easily deterred, and so they are likely to go in and add exception handling to their script. And so it sends students back to the exception handling primer, and then they can at least get a message stating that the image is not a string. And so then they will also be able to see the ciphertext that is transmitted. But they still have to decrypt it. And we'll end up picking this back up in brute force because there are brute force attacks that can conveniently decrypt this ciphertext, especially since there's only 25 different options for decrypting it. It can go pretty quickly. Let's see here. So sniffing without errors. Okay, so then texting with terminals. And this is the same routine where now we're going to send encrypted text. Pardon me. All right. So let's see if this is too long to paste in. This is one where you can run it first in just one of the two microbits. And so we'll pose as a sniffing attacker with the other microbit, hoping that that the user is simply sending an encrypted text. Okay, let's see. I need to give you the web address and then the script. Web address. And if you are going from the web address, remember to add that quotation mark. I'm going to update the script before sending it through the chat. Okay. So when we go ahead and run the, we're going to have to go back and use the unencrypted version of the chat to emulate the sniffer. And that is a ways back in bidirectional texts. So here is the link address for bidirectional texts. And the original oh, look at that. Okay, we're going to have to fix that link. As I mentioned, there was a migration that occurred during Christmas break, and we're still finding a few little things like the ones I'm stumbling across during this workshop. All right, so we want cybersecurity, radio basics. No, not radio data. Radio basics. Continue. Bidirectional texts. So the second microbit, instead of using encrypted, we're going to use the unencrypted. I just pasted in the page and am now pasting in the app for the second microbit, or the script for it. Okay, so the one on the left is the encrypted, so we're going to enter a key, keep it at 5 just for simplicity's sake. And then this one just works out of the chute since it's the unencrypted version. So now, if I'm typing hello over here, we get the familiar MJQQT over here. And I'm just trying to, I know it gets kind of boring to use the same term, but it also allows us to just sort of verify what's going on as opposed to changing everything else up. We're keeping that, or at least for the workshop, I'm keeping that static. And I think it's probably helpful to show the students it this way too. Of course, a student would then immediately pick up that the key must be 5 and they could do their decryption. But if you instead type something longer that, oopsie, longer that doesn't include hello, this hopefully can impress upon the students that ciphertext can seem more difficult to decrypt. And so here is our sniffer. And then what we'll do is just take the encrypted transceiver script and then paste it into the other side. I'll paste it again. So this is the encrypted version. And we'll, pardon me, we will paste it where the unencrypted version was, and then run it. Now we have the intended receiver. And you'll want to remind students to be on their own channels and then to share a key offline with each other. And so assuming that the key is 5 on both sides, then the students can send hello and they'll receive hello. And at this point, I try to emphasize, look, there is an encrypted layer in all this, but there's, but the user experience is nothing different aside from the encryption key, which in modern applications is done using a handshake. And so there we go. And then for the try this, first of all, it always talks about how it works. And then there's a did you know section where there's some various terminology or factoids that are related to the I don't know, did the loud noise from outside my door come through, or was it hopefully filtered out by my mic?
I did not.
Okay, that's good. It was quite a racket on this end. Okay, let's see. So this shows how sniffing works and how it can be mitigated at a very basic level for both an application. Instead of the Countdown app, we used the emoji app, and then we also used there is app data. It's right here. I skipped over that. Sorry. So I'll just paste in the encrypted version of this. Okay, so this is the encrypted version of the Countdown app, which is another one where the same, in this case, the ASCII cipher is used. So I will paste in the, oops. Okay, so I'm pasting in the ASCII cipher version, or the web page, and then here comes the transmitter. I'd better check its syntax first. Okay, that looks like it's working all right. So I'll paste it in. And next up will be the receiver. The ASCII cipher, oh, interesting. The double quotes does appear in the ASCII cipher function, just not in the Caesar cipher function. Quite the mystery, that. Send. Okay, so this one was too long. All right, so I'm going to have all of you simply go to encrypt and decrypt your radio data because the script is too long to make it through the chat in one piece. So we'll have you copy and paste directly from the page into the editor, the microbit Python editor. Okay, and then we'll run them both. Okay, and we can see which one is the transmitter and which one is the receiver. And in the interest of saving a second, I'll cut it down to 3. And basically, if you run, for example, the text receiver script, you would see encrypted script, and so but here even though encryption is going on before transmitting and after receiving, and decryption is going on after receiving, these scripts are encrypting the packet data before sending and decrypting it after receiving. And we can see that simply because here's the ASCII shift key, and going into the main code, it's still doing that dictionary thing it did earlier. And then right here, it starts with, it's already displayed what it's sending. But right here, it's also displaying, or it's encrypting the packet immediately before it sends it. And then on the receiving end, it receives the packet up here, and then it goes into the application, the countdown part, and the very first thing it does after receiving is it decrypts it before it does anything else. And the activity guides through displaying the encrypted part so students can see what it looks like after encryption. And so something like print encrypted, comma, packet. And we can do that on both ends. Make sure to get the indentation correct. That's really important in Python. I might have done something wrong. No. So here we see the dictionary, and then I guess I misspelled liftoff. And then for some reason, did we miss that? Here is the encrypted version of the dictionary. All right, so that's everything in sniffing attacks and defenses. Next up is brute force attacks and defenses. My wife, while binge watching, I think it was Sherlock, found some of our old combo locks that we couldn't remember the combinations to, and she went through all the combinations, and so she performed a brute force attack on all of our combination locks by trying all the different combinations until she found one that works. And that is how I often explain brute force attacks. And so there's a microbit pin pad vault example that's kind of cool. And the way this works is that students use buttons initially to enter a 3-digit binary number. And it turns out that there are 8 possible combinations with 3 binary digits. And that is a super easy combination to crack. And this takes you through the various steps of how to crack that simple combination. And then we change it to a 3-digit decimal value. And then students get to see that there's more combinations. And eventually, they get to try to crack the Caesar cipher with brute force. And then we talk about further strengthening the cipher using a custom cryptobit, and how that makes it really, really difficult to, or much more difficult to break to figure out what the key is. Although there are still techniques that can be used, like examining the repetition of certain common phrases and using that to glean some information about the cipher that's used. So let's see. I think it's kind of fun to try the pin pad vault, and it's simplest form. Let's see here. I wonder if this one's going to end up. Okay, that one went to the correct address. Good. All right, so we'll try this together. Here is the web address with the transmitter script. All right, and then here is the receiver script. Did that come through? Let's see. I'm looking. Bank vault receiver. Yes, it came through. Okay. Okay, now looking at the camera for these, this is a binary 0. And well, first of all, okay, so this is our transmitter, our transmitter keypad, and then this one is our so-called bank vault. And to enter a binary digit, you can switch between 1 and 0 like so. And so, for example, there's a 1, and then it automatically makes your next digit a 1 as well, but you can use the A button to switch back and forth. So if I send 100 or 101, then after I send the last digit on this microbit, it's going to tell me that with an X that was the wrong combination. And so no access to the bank vault. And I want to say that we had some text that's displayed here too, but maybe not. Okay. Try 0, 1, 1. And that is, in fact, the correct combination. And so then students get challenged to choose their own combination and to try the different combinations with a manageable number of 8 possibilities and see how easy it is to crack a low security passphrase or a low security PIN. Now, we also do that for a, and then we see how an attacker might write a script to crack that code. Now, you'll have to be careful with this one because you'll want to put the script to crack the bank vault code into the transmitter. So this was my transmitter script, pin pad transmitter. So now I've pasted in the bank vault crack script. And when I send that, what it does is it presents me with an arrow. It presents me with an arrow pointing to the A button. Yeah, the A button. And when the A button is pressed, it will launch the bank vault crack routine where it tries the 8 different combinations to find the one that will open the bank vault. So we'll go ahead and get that started now. 0, denied. 1, denied. 2, denied. 3, entry granted, or rather access granted. So there's also a nice little counting and binary component to this. And we also do that with a decimal vault pin and a decimal vault pin crack. And then we talk about strengthening pins. And the thing about strengthening pins is, obviously, the more combinations, the harder it is to crack. But there are additional security features that are used. For example, if there are 3 consecutive failures, it tells you you have to wait for an hour. So we could try, I think, this one on the receiver. Oh, we have to, this is for the decimal one. I think we're running a little bit short on time, so I'll just tell you, hey, it's here. So there is a decimal pin vault example, and then another example of how the decimal vault pin can be cracked with a similar script that tries all the different combinations. And then in terms of strengthening the pin, actually, this one I think we can just run on its own. Let's see here. Yeah, there's no radio in this. This is just an example where we're using it in the terminal, and then the students are challenged to incorporate that into their bank vault script on their own. Copy. So here is the address. And if we put that into one of our microbits, oops. Have to go back and get it. Copy. Send to microbit. And so if we do this right and enter the correct code, 324, access granted. But if we make 3 mistakes in a row, like by mounting a brute force attack, then we're locked out. Can't enter any more codes. And so that's an important thing to show the students. And then there's cracking a cipher with brute force. And so this is where we go back to transmitting the various emoji. So for this, the transmitter is sending the different emojis. And the receiver has to, let's see here, share something personal. Okay. So this is the brute force attack on the cipher that is used. And so what we have to do is go back to the encrypted transmitter. So that's share something personal encrypted. This is another one that is missing its apostrophe. So I'm going to correct that and then paste it through to you, or quotation mark, Control AC. Okay, so here is the original share something encrypted in the chat, and we can run that. And then on the receiving end, we'll go ahead and run the brute force attack on the cipher key. Here's the web address for that page. Oh, okay. I apologize. I may have made a mistake here. Oh, okay. So this is a little bit cooler because this is the same one from Send Something Personal Encrypted, but it has an unknown key. And it also has comments with the changes from the original. And let's see if it has the quotation mark. It does not. Okay, so I'm sending this one to you that has the unknown. Oh, gee, it's not letting me send that through either. Okay, so if you want to try this one along with me, just remember to add the quotation mark in the result equals part of the send images, and it looks like receive images is also missing a quotation mark on the result equals line. So I'll demo this and just give you the link, and the two scripts are on the same page, the emoji transmitter and the cipher key crack receiver. Okay, so now this one's sending encrypted. And then our receiver will do the essentially it will attempt to decrypt using all 25 possible, or really all 26 possible Caesar cipher keys, and it will check, and then students end up checking to see if anything discernible appeared in that list. And this might, oh, I forgot to do the apostrophe here. And with 25 different possibilities for decryption, it's pretty easy to find the key. It was randomly selected on the transmitting side. So students will have to go through, as will I, and see if I can find something that is readable in all this? And there it is. The decryption key for this is -20 because I found angry in there, something that is human readable. So that provides an example for students of how cyber attacks can automate decryption of certain keys, and also how weak ciphers like the Caesar cipher make it awfully easy for those scripts to succeed, and can also provide an opening to reinforce best practices with passwords and using stronger encryption keys. Okay, so let's see here. So this does go on into more combinations, and using a substitution cipher and using a random cryptobit, so the ASCII cipher to strengthen it, because that way you end up having to use 90. And then with the custom cryptobit, there's like 26 factorial different options. And so trying to decrypt, so there's a clever little script here for creating a custom cryptobit without doing it by hand. And then students are challenged to go and strengthen some of the applications that were used previously. In this case, the Cyberbot's navigation control from a keyboard. For those who have the Cyberbot robot, they can go ahead and strengthen their custom cryptobit that they use for sending commands that include the runtime and the left and right wheel speeds in a dictionary. And so that is the end of brute force. I skipped a few things, but I think it would have been a little overhurried if we did every single example in here. But I hope you found that to be interesting, and that your students find it to be interesting, and also that it gives a clearer insight into how encryption and decryption works, at least on a fundamental level. This is not AES 256 encryption, but you can use this certainly as an opening to talk about things like that. Okay, so for your homework for Friday, if you did not already have an account on learn.parallax.com, you will be sent an email saying, here's how to log into your account that we've created for you. If you already had an account, see if you can remember your password. If you have any trouble with that, Ari, should we have them email you directly or just send it to education? What would be best there? All right. Okay, so first of all, most of you, even if you don't remember your password, that's fine, because if we go to learn.parallax.com, what you can do is go to the Teachers tab and then log in. There's a link right up top, and I'll email this to you. Now, if you don't remember your password, you can simply click Lost Password to have your password sent to you. If you still have any trouble, or for example, if it doesn't recognize your username for whatever reason, then go ahead and email us. And Ari, which email should we have them use?
It's better to use education@parallax.com, and I send it through the chat.
Oh, excellent. Oh, so it is in the chat right there, education@parallax.com. Okay, so that is it for today. We're going to stick around for a little while, and for any questions and answers you might have after the recorded portion of the workshop. But we're going to stop the recording in just a few moments after I thank you all for coming, and remind you that we will have the next session on Friday, this Friday, at 3 p.m. Pacific time, just as the others have been, and that you'll be using the same link as you have used for the others. Thanks for coming. We really appreciate it and look forward to seeing you again on Friday.